This is a tutorial on how to calculate PI for super cool kids only. You may be asking yourself, what is PI? PI is also called the isoelectric point, and it is the pH in which a molecule's net charge is zero. In biochemistry, usually the molecule that you're looking at a PI for is either an amino acid or a polypeptide. I do not want to scare you away from this video, but I do have to talk about pKa and titration curves. But don't get too scared, don't have flashbacks from Gen Chem. I'm going to break it down super easily and all you need to know for biochem, and you will be fine, I promise. What is pKa again? I think of it as the acid dissociation constant, but it's also known as a half equivalence point, and I'm going to do a little visual that I think will help you. When pKa is greater than the pH, most of the acid is going to be still protonated. It's not going to be fully deprotonated because the solution is so acidic. However, when the pKa is exactly the pH, half of the acids are going to still be protonated and then half are going to be deprotonated. Now, when the pH is greater than the pKa, most of the acid's going to be deprotonated and become the conjugate base. Now, what does this have to do with amino acids and polypeptides? Well, each of the ionizable groups on an amino acid has a pKa. So, at that specific pKa, half of the ionizable group will be protonated and half will be deprotonated. So we can use these pKa's to know what the charge will be of each ionizable group at a different pH. Let's look at how this applies to a specific amino acid, specifically glycine. Now, this is glycine at 3 different pHs, but how would we define or necessarily know, depending on the pH we're given, which form of glycine will be present? Well, we can use our pKa's. Now, these pKa's are useful to us because they tell us that at exactly pH of 2, half of the glycine in our solution is going to be that net charge of +1, and then half is going to have that net charge of 0. Furthermore, anytime the pH is less than 2, most of the glycine in the solution is going to be that net charge +1 glycine. But anytime it's over pH 2, it's going to have that net charge of 0. So we know from the pKa's that between pH 2 and 9.5, the majority of glycine in a solution is going to have that net charge of 0. But we need one pH where all of the glycine is going to have that net charge of 0, and what that would be is the halfway point between those two pKa's. So to calculate this, we can actually take the average of the two pKa's to find out what the pH is when our glycine has a net charge of 0. Now you may be asking yourself, what if hypothetically, and this isn't even a crazy hypothetical because there are several charged amino acids, what would that look like and how would we calculate the PI for that? Well, I'm glad you asked. This is lysine. It has an additional ionizable group compared to what we saw with glycine and alanine, and it uses the same pKa's for its N-terminus and C-terminus side, and then we can get the pKa for its R group just from that same list by looking for lysine. This is how lysine structure changes as you go up the pH scale. So if PI is when lysine is net charge 0, then we need to find out what the average is between the two pKa's that go on either side of that net charge 0 lysine. Doing the calculation, we get that the PI for lysine is 10.15. Polypeptides, same idea, you just have multiple ionizable groups. Now, you don't always have to do this when calculating PI, but if you want a good practice, pause this video and see if you can draw the structure of this polypeptide. Okay, now that we have the polypeptide drawn out, where are the ionizable groups? Okay, so here are each of the ionizable groups that are going to change as our pH changes. And we can find the pKa's of each of these ionizable group by looking at that handy-dandy table. Then write out your pKa's from least to greatest, and then write above those pKa's what the charge will be when it's less than that pKa and when it's greater than that pKa. I'm going to show you what I mean. From here, it's a little bit more intuitive to figure out how we're going to calculate the PI. We find those pKa's that are surrounding when our net charge is 0. We take the average of them, and then we have our PI. We did it! So here's another polypeptide. Feel free to draw it out if you like, or what you can do once you get a little bit more advanced is just write out those pKa's in ascending order and then figure out what the max charge is going to be and calculate the charges between each of the two pKa's. So once you have those all written out, then you just find the two pKa's surrounding when the net charge of this polypeptide is 0, you calculate the average of them, and then you have your PI. Doesn't that feel super, super lit and cool? I hope you feel it because I feel it. Now, don't you worry if you still feel like you need practice. You can find a ton of practice utilizing your resources, aka ChatGPT. You can literally just type in, hey, give me a polypeptide so I can practice calculating PI for. It'll give it to you, and then it'll show you the steps on how to do it. So do it on your own first, compare with what ChatGPT got, and you're on your way to becoming a PI master.